If you
This
look at
conference
because
will now be recorded.
Here, if you look at the, suppose if you take the inductor, is we have only one inductor, and if you look from the inductor terminal, you can calculate the effective capacitance. Like example, in case of source, we say it is a short circuited, then the CS and CP will become parallel, right? And we'll have one equivalent capacitance, and that is in series with the inductor. Okay, so the same circuit, but based on the excitation, if it is a current source for the second circuit here, right side, so this will be resulting into the parallel resonance. Okay, so this particular circuit, I mean, today just I'd like to cover on the single circuit shunt compensated lines. So that will be mostly resulting into this kind of network. That is a left side diagram. Like example, I will tell you here. If you have a line and we write a three-phase system, and if it is a one phase, we have the shunt reactor connected. I mean, all three phases will be there, but you take one phase here, and CP and L are the one particular phase. But the CS could be the interphase circuit capacitance, means between phase to phase also there will be capacitance, and so that you have the some source from the other phase is fed through this capacitance to this network. Okay, so this particular thing we are going to look at today, and the applications also we'll see. I mean, why we'll get into this kind of problem in case of this EHV transmission system operations. So can you go to the next slide? Now just look at here the shunt compensation, because most of the lines, because we'll be using to transfer the bulk power for the long distances. I mean, not compared to the HVDC, but in case of HVAC, also we'll be having some long lines at EHV system, like 400 kV or 765 kV, around 300 kilometers, or maybe more than up to 400 kilometers. We have HVAC system, I mean, transmission lines. So generally, in order to limit these steady state over voltages, we propose or we use the shunt reactors or line reactors. We can connect to the line to limit the steady state over voltages. Now, once we have the shunt compensation and long line, and if there is a possibility of this uneven phase operation, means if you have any stuck breaker operation, or maybe some one pole is open and other two might be closed, like that operation can come. Okay, so that is due to two things. One is intentionally we do, that is normally we use this single phase tripping schemes. In case of EHV transmission lines, we use the single pole auto reclosing phenomena, right? So that is what the single phase tripping schemes. So basically the idea is to improve the system stability, because you know, right, like our tower design mostly will cause SLJ faults, not phase-to-phase faults, because the sufficient phase, the clearance between the phase conductors. So there will be very remote possibility to have the phase line-to-line faults, or maybe triple faults, but mostly common faults are phase-to-ground faults, and those faults can be temporary in nature. So we don't want to trip entire circuit for the in case of single phase to ground fault. So that faulty phase can be tripped, and other two healthy phases can carry the some power. So that if you look at the mission point of view, because now there is a corridor is available with the two phases with reduced power flow on that particular line. So that will cause the reduction in the acceleration power for your synchronous motion rotor, so that thereby there is a improvement in the stability, because you will have some margin more. Okay, so that is the idea to have the stable system. So we'll be adopting this single phase tripping schemes. So this is what intentionally we are trying to create this uneven phase operation here. So unintentional here, there is a misoperation of circuit breakers. Like example, in EHV system, we use the single pole breaker concept. Means each pole is having a independent mechanism to operate. So definitely we cannot close simultaneously, and so there may be delay will be there. And if at all any problem in the mechanical side, so there may be stuck. So this can cause this uneven phase operation. Like in this example here, the diagram whatever I have shown here, if you look here, just there is a shunt reactor here, the 3-phase, and we have the capacitance like for each conductor phase to ground capacitance, and between the phase to phase all those things. Okay, so now suppose if you just take one particular phase, the C0 and L whatever is marked here, and somebody suppose if we calculate, right, again if you just calculate what is the equivalent impedance, that is nothing but here these two are parallel, right? That C0 and L positive here is a parallel combination, and if you just simplify into this right hand side this formula, it will be having some relationship in terms of C0 is where zero sequence capacitance, and C plus is the positive sequence capacitance of the line. And this is just only assumption is that line is assuming ideally transposed, then we can derive this kind of simple analytic expression. So from this we can see here in the denominator we have something like a ratio, right? The C0 by C plus, and again there is a K by 100 where K is given as the degree of shunt compensation. Let us say example we say like 50% shunt compensation means the line capacitance is 50% compensated, and remaining 50% will be there for generation, right? So that is the just ratio here, and we are just taking this one. So looking at these values, now this is the equivalent impedance, right? So the top you can see it is J omega L, so it is inductive, but the denominator could be positive or negative based on this the ratio. If it is a negative, then it is a capacitive, and if it is a positive, then it is an inductive. Okay, so I mean that equivalent impedance. Oh, just can you go to the next slide? Then we can we'll get into these three situations here, the based on the degree of compensation. Okay, this ratio, let us say K by 100 less than C0 by C plus ratio. Okay, so generally in case of overhead transmission line, the ratio of C0 by C plus, I mean zero sequence capacitance to the positive sequence capacitance will be around 60 to 70%, right? So 60 to 70% value of positive sequence is equals to the zero sequence capacitance in case of overhead lines. So if your degree of compensation is less than that 60%, okay, so this is the positive, right? That ratio. So this becomes sorry, it is a negative. So this becomes a capacitive, okay. And in case if your degree of compensation is higher than this ratio, means let us say 65, and your C0 by C plus is 60, then you have the that is a positive will come in the denominator, and this overall the equivalent impedance looks like a inductor. Okay, so from the previous circuit, let us say suppose in case of single phase open, that is whatever that if you, because of the auto reclosing phenomena, if you just open the single phase, and we have what I explained that circuit, right? That first one, the series resonance circuit with the excitation voltage. So in this case, what will happen based on this? Maybe I'll just can you go to the next slide? Yeah. So you can look from here. This is your same diagram. Just when you open the single phase from the phase A here, so what are the Z equivalent is calculated here, and assuming if your degree of compensation is more than your I mean around more than that ratio C0 by C plus. So this what are the Z equivalent? Nothing but inductor. Okay, and you can see these sources are fed from the interface capacitance values. You can look from the right side diagram. So if you just take this source and capacitance equivalently can be again reduced to the one source and capacitance and a Z equal. So the Z equal is nothing but inductor and this capacitor. So in case of single circuit and this single phase operation, or maybe two poles opening from the both end, right? So will be resulting into this based on the degree of compensation, will be resulting into the series resonance at a power frequency. Now let us look at the diagram here. This is a single circuit tower with a horizontal configuration, and where you can see this a blue curve and a pink one, where U1 means it is a one phase open from the both ends. Okay, only one phase is open. So you can see here the over voltage on the open phase. Always this over voltage can result on the open phase, because what are these closed phases tightly controlled or controlled by the source, right? Because source is strong, whatever voltage is there, that will be appearing on the B and C phase. But what are the phase which is open, which is decoupled from the main source, but only fed through the weakly fed through this interface capacitance. Okay, so there may be a possibility of your resonance, like in case of a single phase, we have for this circuit, there is a resonance at exactly at 89% of compensation. If your line is 89% compensation, see generally in 400 kV we say like 50 to 80% compensation is possible. But if you look at 765 kV lines, definitely we are doing the 100% compensation, more or less 90 to 100% range, because that capacitance value is very high and it will lead to the very high steady state over voltages. So that's why we use almost 90 to 100% compensation in case of 765 kV lines. Okay, but the question is mostly 765 kV lines. Most of the time it will be double circuit line. So double circuit line, the resonance phenomenon will be different little. I mean that we are not discussing here. But in case of single circuit line, we can see here there is a resonance point where you can see that infinite voltage. So otherwise 89%, and these are the red curve, it is showing the 1 per unit voltage, and around for the single phase operation we can see 78% to 99% degree of compensation range. The voltage on the open phase will be more than your 1 per unit voltage. So that is what it is going to damage the equipments because of this high voltage. And in case of two phase, we can see here the compensation has moved, okay, to the 78%. From the 89 to the 78%, we have the perfect resonance, where you can get the theoretically it is the infinite value. Okay, again it is the range is there 68 to 89%. Also will get more than 1 pu voltage. Okay, so these are the very harmful voltages which is more than 1 pu, because if you don't detect this condition and complete trip the circuit, the equipments which are connected to the line can get damaged. The next, just on 1 minute. So here in this diagram, what we are trying to see that nowadays we are also getting this mixed overhead and cable in the rural area, where we have some of the overhead connections replaced with the cables. Okay, so sometimes even outside also, I mean in the urban as well as rural areas. So there may be possibility of you'll get the mixed overhead, because again cable, if you use, there is a big capacitance value will be there. So in that case you may have the degree of compensation also much higher, because cable generally will try to compensate 100%. Because of this, otherwise you cannot load the cable in case of because of this high leading capacitive current, right? So you can see here from this diagram, in case of single phase opening for the mixed overhead circuit, so it is around 90%. There is a resonance point with the blue, where n is equal to 0, and if you increase like a percentage, right, the 10% underground cable and 30%, so your resonance point is slowly moving towards more than 90%, and also the magnitude of voltage you are getting. So like example, in this red one, it is showing only 1.5 pu. Okay, so at a higher, almost close to 100% compensation, there may be possibility of getting the resonance point with a high voltage. Little higher, maybe 1.5 pu. Also, that is also very dangerous if you prolong for the 10-second duration or anything. Okay, so this is the one factor. Then the next is the same resonance and shunt compensation EHV lines. So what is the effect of neutral reactors? Like generally, if you look at the shunt reactor, generally we previously we have shown here this solidly grounded this neutral point. Now we have added the one reactor in the neutral point here. So again, you can calculate the what is the equivalent impedance now, right? So whatever we have seen in the without a neutral reactor, where we have got based on the degree of compensation, this equivalent impedance can be either capacitive nature or inductive nature. Now we have this formula here, so where your ln is added here. So we have seen, right? So if the equivalent impedance becomes inductive, then there is a possibility of resonance. Otherwise, if it is a capacitive nature, there is no problem. Then what we are trying to do here, can I add some minimum neutral reactor such that this equivalent impedance becomes a capacitive? There is a minimum neutral reactance so that I can add, so that the equivalent impedance becomes a capacitive nature, and there is no possibility of any series resonance, because capacitor in series with again one more capacitor will not cause the resonance problem. So maybe you will have some reduced voltage induced on the open phase conductor, but that voltage is not harmful for the line, because it will be definitely it will be less than 1 pu voltage, maybe 30%, 40% might be there. Okay, that is the one way of calculating this neutral reactor minimum, how much is required to avoid this resonance point. Okay, then next there is a one more approach to calculate the neutral reactor considering the even degree of compensation. That's what we are showing here, L and even K. The degree of compensation here, see, you look at this diagram, where we are showing the C0, right? That is the zero sequence capacitance generally is equal to the phase to ground capacitance of the line. Okay, so as I said, it is a 60 to 70%, right? And of the positive sequence, right, value, and our degree of compensation also may be 60% or 50%. Okay, means there is a uneven compensation with respect to the sequence components. Let us say, suppose if the reactor is bank type or maybe the shell type construction for three-phase reactor, means there is no mutual coupling between the phases, means positive sequence and zero sequence inductance value of the reactor will be same. So when you compare with this capacitance, positive sequence capacitance, it is only compensated 50%, but zero sequence capacitance, because the value, let us say 50% compensation, and the zero sequence value is 60%, means almost we are compensated around 90% of the zero sequence capacitance. Okay, because that is the default will come with uneven compensation between the positive and zero sequence capacitance values. So in order to make that compensation even, so that we can add additional neutral reactors so that it will be equal. Okay, this is one. The third one is the minimum secondary arc current. Like example, in case of the single phase stripping or auto reclosing phenomena, we are utilizing whatever this single phase stripping, because as I said, like faults are temporary in nature. So once you trip the from the both ends, so whatever this current, right, it will be reduced, because there is no strong source feeding that fault current, because from both ends that fault is both end breakers are open, particular poles are open, so there is no current, right? That current will be little based on the recovery voltage induced on this phase conductor will flow. So that generally will be in terms of 100 amperes, 200 amperes, like that. Generally your fault current will be in few kiloamperes, like 2 kiloamperes, 5 kiloamperes, 15 kiloamperes, but this value will be around 100 to 200 amperes range. Okay, whatever, with compensation, without compensation, whatever, in that amperes range will be there. So if you want to get the successful auto reclosing phenomena, that secondary arc current should get a self arc extinguishing, right? So for that also one application where we can use this neutral reactor to reduce the minimum secondary arc current. So that is again a formula is given here based on this, but these formulas are valid only for the ideally transposed line, so that we can directly design what is the reactor values required. Now let us go to the next slide. Now this resonance in shunt compensated lines, what is the effect of transposition? Okay, let us say suppose if you take the horizontal tower, same thing. So we have the external phases and middle one phase, right, for the horizontal configuration. So here you can see here for the external phase, the degree of compensation, the resonance point is moved, right? And similarly, if you go for the two-phase operation, where like external and central phase here, then the two-phase this thing, okay. So here also you can see that this resonance point for the ideally transposed lines, we are getting only one particular location. But in case of for untransposed lines, we'll be having some range of degree of compensation. There is a possibility of, like example, phase A, phase B, phase C, that is a single phase opening. You may have different resonance points at the degree of compensation. So in practical cases, definitely no line is ideally transposed. Generally, we'll be having the section-wise transposition, or maybe selected locations we have the transposition points. So definitely it will be will be having the main impact. Okay, now just to summarize, what are the parameters which are affecting the resonance? Like example, network strength. That is a meaning of we have the different fault levels in the system, right? If you take the 400 kV bus, we say it is a 5000 MVA fault level. Okay, so this is there is no impact on the source strength, whether it is a weak source or a strong source. There is no impact, because, as I said, this is the resonance is going to appear on the only the open phase conductor. Once the conductor is open from the network, so there is no impact. The next, tower design. So this will be having again marginal, because most of the practical tower designs are having the, standard tower designs will be having the same the range of capacitance. However, based on this, sometimes if you don't have the right of way, with the minimal changes for the towers, sometimes we'll be upgrading the one voltage level to the next higher voltage level for the same old tower. Like example, if I'm used 220 kV tower, but with some minimal changes, the same 220 kV tower can be extended to the 400 kV tower. Okay, so what will happen, because that looks like a compact compared to your regular 400 kV tower, this may look like a compact. So if the tower design is a compact design, means if a phase conductors are placed very close, then your capacitance values will increase. Like example, in case of a cable, we have the uniform that, right, and trefoil formation for the cable. So generally, if you take in the practical condition, people will go with the trefoil trefoil configuration, because trefoil configuration conductors are placed next to each other, and it requires very minimum right of way when you compare with a uniform placement. But because the right of way is the big problem, but problem is the trefoil will increase the further capacitance when you compare with the uniform placement. The same way here also, tower design also, if you go for the compact design, definitely it is going to increase your capacitance values. Then obviously that is going to because we have seen, right, this coupling effect is due to capacitance coupling as well as inductance coupling, but inductance coupling will be very minimal, majorly dominated by this capacitance coupling. The next, circuit asymmetries, whatever we have seen now, this will be again a high value, because the untransposed lines will be having different characteristics compared to the fully transposed. The next, magnetic saturation of the reactor core. So where we are using the shunt reactors or line reactors. So this also will be high, because this is going to change the inductance value, right? Once the reactor gets saturated, that inductance value is going to change. And whatever we have seen that inductor is also participating in that network, so that is going to change. Basically, because once the saturation it occurs for the reactor, the inductance value will come down. So this is going to reduce the amplitude of the overvoltage magnitude. Okay, if it is not saturated, it may generate very high values. If it is saturated, it may reduce to whatever we have seen, like a theoretical resonance point, it will be infinity. but with saturation point representation, voltage magnitude may be reduced to 2 per unit or 3 per unit, even at the ideal resonance point. The next saturation knee point, this will be again, as I said, like saturation is having high impact, but it could be medium or high, because if you compare with the transformers, the saturation knee point voltage will be much higher, because transformers will be having only 1.15 or 1.2 pu is the knee point voltage, but in case of reactors, generally at least it will be 1.5 pu and above, like 1.7, 1.8 pu will be the knee point voltage, because there they use the gap cores, so we'll be having a high value to reach saturation. Then reactor core construction, this is also very important, because if it is a bank type, there is no mutual coupling between the phases, means you have both positive sequence and zero sequence inductance values are same. And if it is a three-phase transformer, three-phase shunt reactor with a three-leg design, so definitely there will be a strong coupling between the phases. And like example, 80 to 90% of positive sequence value will be your zero sequence inductance value. So that is also very important, based on the construction. The next, installation of neutral reactor is also having very high impact. So it can detune completely. Suppose if you have some resonance at one point, by adding this neutral reactor can detune, so that you'll will not have any over voltages. The next, the neutral resistor also will have the very high impact. So this is basically, this is going to provide damping. So this damping also is going to reduce the, so because basically this resonance point is basically weakly fed through the source, right? Because the capacitance reactance value will be very high at a power frequency, right? So we'll just say most of the time we'll neglect the strike capacitance of the equipments, because at power frequency the reactance value is very high, right? So because of that, this whatever additionally, if you put some resistance, the damping is sufficient to take out those oscillations in the I mean, whatever the energy is there in the oscillations can be taken out, so that the oscillations can be eliminated. The next, installation of cable sections, where we have seen like hybrid lines are with mixed overhead lines and cables is also having a very high impact, because if you add the cable, then the degree of compensation will vary very drastically. The next, size of shunt reactors, this is also very I mean, critical parameter, and because where we have seen like in case of single circuit line, if the degree of compensation is less than 60%, there is no problem. There is no, we don't get any resonance problem. But in case if it is higher than 60%, what are the degree of compensation is greater than C0 by C plus ratio, then you have the very high possibility of getting the resonance. And this grading capacitors, in case of capacitors, I mean circuit breakers, there is no impact. And the flows on energized phases, this is basically based on the power flow. So there is a current flow, and because of this inductive coupling, there is again induced voltage on the open phase conductor. Some value will be there, but that will be, when you compare with the capacitance coupling, it will be neglected. So it will be not having much impact for the, at least for the single circuit lines. So maybe in case of a double circuit line, we will be having a impact, because if you take the double circuit line, one circuit out of service and one circuit is in service, and during that time, if any fault occurs on the first circuit, I mean whatever the healthy circuit, so there may be a huge induced voltage effect in a zero sequence mode. Because if you take in a double circuit line, always there will be a zero sequence coupling, but positive sequence wise, the both circuits will be independent. There is no positive sequence coupling, but there is a zero sequence coupling between the two circuits, inductive as well as capacitive. So that there it will be having a huge impact in case of double circuit line. Just can you go to the next slide? Yeah. Yeah. So So we have just seen that these neutral reactors or neutral grounding reactors are going to help to avoid this resonance point. Okay, so now just I think I just logged through my laptop. Can somebody give me control?
Sure, Veerabrahmam. Just give us a second.
Yeah. Right.
Mr. Veerabrahmam, you are the organizer and presenter right now. You could share your screen.
Yeah.
Thank you. And I guess that you may have to disconnect from your mobile to avoid echo.
Yeah.
Thank you. Thank you.
You're able to see, right, my screen?
Yes, but you may have to go to the presentation mode, please.
Yes. Yeah. So
Yes.
now just I would like to give some guidelines how to select this NGR, and based on this, because we have seen like no line is ideally transposed, so that we cannot just calculate using the simple analytical formulas. So we have to conduct studies for this in a detailed circuit representation.
Mr. Veerabrahmam, sorry for interrupting you. I think there is a disturbance in the voice. So could you come closer to the mic if you don't mind?
Yeah, I have put headphones only.
Okay. Okay. Thank you.
Yeah. Okay, so first with this equivalent network representation. So in order to carry out for the NGR guidelines for this single pole auto reclosing phenomena, so we need to just represent at least two bus equivalent where these equivalent sources represented with the short circuit levels, and the transmission line is modeled with the detailed untransposed structure, and shunt reactors also can be modeled with either zero sequence, I mean phase coupling between the phases, mutual coupling between the phases. Then we can do the next steady state analysis, where we can do the single pole reclosure studies to find out what is the recovery voltage and the secondary arc current. Okay, so that we'll be see basically this NGR will not be designed for the resonance problems initially. I mean, while designing, because our main aim is to have the successful auto reclosing phenomena. So that is the main aim. So how do we get the successful auto reclosing phenomena? Means we should have the minimum secondary arc current and minimum recovery voltage, and rate of rise of recovery voltage should be maintained some range, so that we will be having our arc extinguishing is possible successfully, so that we'll be having successful auto reclosing phenomena. So first we need to find out by varying the NGR value, and we can do some steady state analysis here. Then next selection of initial NGR value based on the steady state value, and using this initial value, again you conduct a transient analysis where we can see that for the selected NGR value, whether this arc can extinguish automatically. Okay, then finally we have to provide recommendations or technical parameters for this neutral grounding reactor. Okay, so in steady state analysis, we do this single pole switching. So just you create a fault. I mean, this is a constant fault, and open the from both ends and try to measure the secondary current. And next steady state the recovery voltage. So without fault, just only open the poles and see the how much the voltage we are getting induced on the open phase. The next we'll be calculating the triple RV under this same single pole switching operation. And for this each operation, we'll be also measuring the neutral point voltage and current, because we have to define the neutral voltage class for the reactor. So thereby NGR also there will be a voltage class. So once you define the voltage class, we can select the BL value based on the different fault conditions later. So here these values will be recorded by varying the your NGR value. Generally, we consider NGR value in terms of percentage of the phase reactor value, like a 5%, 10%, 15%, 20%, like that. In steps, you can vary, and you can record all these things, and you can just note down these values. Then afterwards, again, we can also do the stuck breaker condition. So this is basically we are trying to see that is there any possibility of getting resonance, right? Because whatever that NGR value we are going to use, that should not cause any resonance value. So in steady state also we can calculate. So basically these studies can be done using EMTP type software, but we have to run in the till the steady state mode till to reach the steady state. So then you can record these values. So basically here the stuck breaker operations are uneven phase operations. We are trying to see that we should not have any resonance at any neutral grounding reactor value. If it is there, we have to avoid that, because now we have done the single pole studies and stuck breaker operations in steady state, and based on this these two values, we can initially choose this some NGR value. Like example, in case of 400 kV systems, these are the minimum requirements. Like your triple RB should be less than 10 kV per millisecond, and secondary current is less than 40 amperes is a peak value. Okay, so in case of double circuit line, we have to also use this induced voltage on the DNAJ circuit under normal operating condition as well as fault conditions. So after finalizing, after choosing some initial NGR value, we'll go to the transient analysis. So where we study this the secondary or current quenching, because we have to identify the dead time, right? Generally, we choose. Practice is that dead time will be allowed up to 0.7 to 1 second range. Okay, that depends. But in India, at least we are using 1 second. Outside, people are trying to use even lesser time, up to 0.5, 0.7 they are targeting. That is the dead time to have the successful order closing phenomena, right? So for the selected NGR value, whether we are going to get, okay, so then here we need to model the arcing fault, so that automatically this arcing fault extinguish automatically, so that it will ensure the successful recloser. If it is not getting, then maybe the initial value is not sufficient. Maybe we may have to go to the next higher value where we will get because this is our main objective, right? To have the successful order closing phenomena. But the only thing is, once you identify that particular NGR value to have the successful order closing phenomena, and we have to check again, it should not cause any resonance problems under different stuck breaker conditions. Okay, so that is again we have to cross check here. So this temporary overvoltage studies again come under the transient analysis. So this is going to select based on the during the single phase to ground fault. So what is the voltage rise on the healthy phases? Because this is basically we are looking at the neutral point to design the surge arrestor rating here, because we'll be using surge arrestor at the neutral bushing. So for the production of the neutral reactor. So from this study, we are going to arrive the rating of surge arrestor. So general thumb rule is uh, means we can do a single phase to ground fault at the open end line. Means don't connect any. I mean because open end line means it is a Ferranti effect, right? Some over voltage will be there. So at that time, if you create a single phase to ground fault, there you'll get the maximum neutral voltage. So that maximum neutral voltage, I mean, your arrestor should not operate for that because that is a temporary in nature. Maybe it may be there for the 1 second to 10 seconds based on your what are fault tripping this thing. Because for the design point of view, we have to wait for a long duration, 1 second or 10 seconds generally, which is the short time rating, right? That voltage values. So we can select the surge arrestor rating based on that particular value. The next, the switching over voltage is again with the line reactor. The switching over voltage are random in nature, so they may get more voltages after adding this neutral reactor. So again, it is necessary to run switching over voltages means by energizing the line with along with the line reactor and neutral reactor, so that you'll be having very, I mean, you should not have any very high switching over voltages, because right, in EHV system the switching over voltages are very critical for the insulation coordination point of view. Because if you just take the 400 kV network, 400 kV system, we have the switching impulse level is like 1050 kV. So if you just find out what is the per unit value in terms of the system rated voltage, so it is around 1050 divided by 326 will come around 3 to 4 pu, right? I mean less than that, around 3 pu value. But the switching surges can occur maximum theoretically up to 4 pu. Okay, considering the trap charges when you do the line re-energization. So that 4 pu maximum possibility, maybe including this the line resistance, attenuation, all those things, you may get around 3.5 pu value. So, but your insulation is provided only 1050 kV. I mean, in this case, around 3 pu. So, there is a possibility of getting the insulation failure for the switching over voltages. So, now just our objective is to check that the switching over voltage after adding this neutral reactor should not increase further. That is like a verification. So this neutral reactor, these are the typical parameters, technical parameters to be specified from the study. So what could be the your rated impedance at what are the frequency, right? Based on that inductance value, we can calculate. Like example, in this case, we are showing like 600 ohms. The rated current, this is 10 seconds. What is the rated current? This is like a short time rating. We have to tell, right? Because some these stuck breaker conditions are maybe during the ground faults. So maybe your system should be designed for this short time rating of 10 seconds to withstand for this much current. And there may be a continuous current, because this always little bit unbalance will be there in the system voltage. And whatever that unbalance is there, because of the unbalance, there is a flow in current flow in the neutral, right? So that is the one. And there may be unbalance in the reactor design itself. If it is a 1%, 2% unbalance between the phases, also can cause some current flowing through this neutral reactor. So that should be continuously to withstand for this. So that also we have to just calculate. And sometimes you can also take the worst case, like example, we have the breaker, only one pole is closed and the two poles got open for the reactor breaker. Okay, what will happen? The entire voltage is appeared across the phase reactor and neutral reactor. So that is also like a stuck breaker condition. So that also we have to define the short time rating, how much. So this is basically short time current, and rated impedance will give you this rated value here. Then peak current rated, so how much it can withstand for the peak currents. So because these reactors will be having very high expiry ratios, maybe like a 50 or 75 like that. So there definitely the big DC offset currents will be there because of this high expiry ratio. So the design should withstand for these higher values. So this is like you can also get from the studies. Then power you can just calculate from the VI, whatever here is given. Then afterwards, the important thing is the insulation class at the neutral point. So this is again based on the fault voltage criteria, whatever I explained, like at the open end you create a single line to ground fault and measure the neutral voltage at the reactor, and that you use as a to define the voltage class at the neutral point. Like this example here, we have the 69 kV RMS. Okay, as for the IEEE standard 39 is design. I mean for the neutral grounding devices design. So once you know the fault voltage criteria, I mean using the fault voltage criteria, once you get the voltage class, once you know the voltage class, we can find out appropriate the BL value. So generally, this is for the reactor. So the shunt reactor also will be generally graded insulation will be used because phase to neutral the value has to come, right? So let us say suppose if you start from the 1300 BL value from the phase, then till the neutral point it can come to up to here 350 kV peak, right? So 1300 kV to 350 kV is the graded insulation for the phase reactor. Then 350 kV to the ground point, here we are doing the 15 kV RMS. Okay. So then further surge arrestor also can be suggested based on this 10-second rating. We can propose the surge arrestor, because we have to check the surge arrestor temporary over voltage capability for 10-second rating. You can select example like in this case for 10-second rating 84 kV we have seen, right? So we have to select a surge arrestor such that the 10-second voltage rating should have more than 84 kV. Then we can select the corresponding rated value here. In this case, example is rated value is 78 kV, like that. So now let me just quickly go through some simulations. Okay. So first I will just demonstrate the resonance simulation. I'll be using one typical example of a 400 kV network with a 300 kilometers with the different degrees of compensation, where we can see the whether resonance will be there or not for one phase, two phase. So you're able to see, right, MiPower screen?
Yes,
Hello.
Brahmam.
Yes. Yeah. Okay. Thank you. Okay. See here. Just I have modeled one equivalent source here. Then we have the breaker. Then we have reactors. Since it is a 300 kilometer line, just I took both side compensation. Like an example here, this 50 MVA reactor, if I use, the degree of compensation is 47.7. So as I said, like for the ratio, right, C0 to C positive is around 60 to 70% range for overhead line, and which is less than this degree of compensation, right? The 47.7% compensation is less than your the ratio of, for this example, it is a 65. So definitely we don't get a resonance problem in this circuit. The next second case here we'll be having 80 MVA reactor here for the long line. Then degree of compensation is coming around 76. Okay. Then we can also see in the third case for the same 80 MVA reactor. So just to show that if I use, I think I have explained 3 different ways of the neutral reactor calculation analytically. So just we are just concentrating on the resonance. This is the minimum reactor, minimum inductor is required only 2.5% of positive phase reactor value. So this is around 55 ohms. This will just try to see. Just a minute. Let me check. This is a 2-phase. First, let me do single phase opening. Let it be 2-phase. I mean, I think net. This reactor with solidly grounded. Okay, neutral grounding is not there, and it is a 50 MVA. And this also here we have 2-phase. Oh, okay, here I'm showing 2-phase opening. Okay, this is a circuit breaker where we are using the single pole operation, and each phase wise we can control, and the phase C is in closed condition. And here I put 55 ohm, right? The minimum value, and this also I think it is okay. It is a single phase. This also I'll just change to 2-phase operation. So, okay. So just we are trying to observe some bus voltages here. Like 2 phases we made, right? A and B phases for all the circuits with the different values. So this degree of compensation is different for the first case. Next. Okay, you can see here this blue one, right? Bus 1, 2, where you can see that is the case 1. The degree of compensation is less than your ratio. That 47.7% is less than that this value. Okay, that is the what bus 1, 2 is here voltage. Okay, this is the system. We are trying to monitor that one phase. Just what are this open phase? I plotted for only phase A here. You can see here there is a recovery voltage is there blue, but it is not higher than our rated value, right? It will be less than this. Okay, this is not harmful for this. The next green one, this is a 22. That is something like a second case here. So the same point I'm measuring, but this is the, you can see here the degree of compensation is higher than this. So definitely you'll be having some resonance point where you can see the voltages. So how much they are touching? 1572 kV for the phase 2 ground values. Okay. So if you still you can also there will be the low frequency superimposed. Okay, something because of this network L and C values. There is something called a bit frequency. Will be always having. Let us say. Just I will tell. The next we can see here the red one. Little higher than your rated value, but because we have used only very small the 2.5% value whatever we have used, and that value is valid for the single phase stripping, so whatever the formula. But this is not able to completely due to your two phase opening resonance point. Now let us say suppose I will zoom it a little bit 1.8. Okay, so you can look let us say blue one here if you see it is a 1.855 and this is around 1.876. So approximately this is also around 20 milliseconds. So means you can look at the green one. There is a, a resonance at power frequency itself. Okay. Okay. So this is the just single circuit resonance where we can see here the degree of compensation, because see here you don't get for both even single phase and two phase you don't get, but in this case both phases you'll get resonance point. So just I will this is the just to understand the concept of the resonance phenomena for the uneven breaker pole operation. Now let me go to the let me open the other case. Okay, so here that's what are this I explained that a steady state analysis where we do the stuck breaker operations and single pole analysis. Here we'll be doing it opening at 0.2 seconds, and we are creating the fault at line. This okay, this particular phase A is opened here, and this could be some reactance, right? I just model here 220 is 10% value. I mean, you can vary from the 0 to this thing, and now we are going to this is calculate the secondary arc current. So I'm just creating single line to ground fault. This is a constant fault. Just I'll just try to show the so where you can just a minute.
Just 1 minute. Okay. Just you can see here. This is a fault duration, right? And we have removed the fault. At the same time, we are also opening the poles. So this is what actually recovery voltage is coming. And from this recovery voltage, we are trying to calculate even the triple RV. And this is a steady state. If you do the normal single pole opening, we'll get the steady state values, recovery voltage. And from this graph, we'll be calculating, like example, I'll tell you, from point 2, we are clearing the fault. And, this will be so from the fault clearing point, from initial 6 to 8 milliseconds, if you do the dV by dt of this particular curve, what will be the maximum value around 6 to 8 milliseconds? That value is treated as a triple RV. This is the triple RV calculation, and just now suppose if I don't remove the fault, let it be hanging. So this will give you, but same single pole tripping is happening. Now we'll be getting secondary arc current. Just I will show. Okay. So this is the at 50% fault location, and this is our fault current. This is like a primary fault current during the source feeding. Then once the switching is happened, so this is what we call a secondary arc current. Generally, this one you can zoom it. Okay, so this is what secondary arc current will be small value in the range of around this 40 amperes like this. Okay, so you have to measure the secondary arc current and RRV to get the initial value in steady state, where you can take from here. Okay, the next like this, you can also do the stuck breaker operation, and we can measure the recovery voltage. And is there any resonance problem? We can do in steady state. Next case, just open transient this thing. So here just I put two different cases. What is the effect of the series capacitor? Because it is a long line, also will be having series compensation. So to tell that in case of series compensation, the secondary arc current will quench, I mean, damp very slowly compared to this normal line. But shunt compensation is very in both the cases common. So here you can see so I'm just trying to create arcing ground fault on both the lines. Just this case, I would like to just show that hello. Yeah, I think just this is the last case. Just I will stop after this. So just let me show that the arc current for both the cases. You can see here this green one where I can just okay. You can see here the green one is taking more time to quench the arc current, because this arc current is like it looks like a nonlinear current, like it's not a pure sine wave, right? It's having a nonlinear current. So this is what slowly the arc current is reduced, and your dead time you will get clearly here, right? That from 0.2 to within 3 to 400 milliseconds, the current is cleared automatically. So we can use this safety factor, and we can propose whatever 0.7 seconds or 1 second as a dead time. Okay, fine. I think okay. I will stop it here. The temporary and switching I'm not able to run now. I think difficult. Hello. Hello.
Yes.
Hello. Yeah, I think I'll stop here for the MiPower simulations. I think time is already exceeded 10
Yeah,
minutes.
yeah. Good evening, everyone. I'm Avik from PRDC. We welcome the floor to for some questions from the participants.
Yeah.
All participants, if you have any question, you can ask them here. Okay, fine. So we believe at the moment there are no questions from the participants. So thank you, Mr. VEERABRAHMAM, for this wonderful session. To all the participants, our next webinar is scheduled on next Thursday, December 24th, 2020. And the topic for the next webinar is power system protection using MiPower. and this notification will be shared on our LinkedIn page as well, and also it will be shared over email. The feedback link for this session will be shared to all the participants over email, and you can share your feedback. And henceforth, we'll share the video of this session.
Avik, are you able to hear me?
Yeah, Divya, you are audible.
Oh, thank you so much, Avik, and sorry about the inconvenience caused because of the glitches and the technical issues here. We have a couple of questions, Mr. VEERABRAHMAM. If you're available, would you like to answer these questions
Yeah, sure.
before closing? If it is okay with the audience also.
Yeah, okay with me, no problem.
All right, thank you so much. And the first question is from Mr. Tariq. Does it mean that designing a filter means making electromagnetic energy compensated with electrostatic?
Yes. Whatever this capacitive coupling, we are nullifying through this reactor, so that that resonance point we are detuning, and in case this recovery voltage, I mean, whatever the induced voltage and the open phase will be reduced. So once if you don't have voltage, then obviously the secondary arc current also will reduce, and you will have your arc will automatically quench. Yeah.
Okay, thank you so much. I hope that answered the question. The other question is from Rashmi Shekhar. For defined line length and specific conductor type, whether the NGR value will be the same, or is it does it depend on the fixed reactor value?
Yeah. It will not be same. It will change, because that depends based on the line length and degree of compensation. Then accordingly your NGR size will come. Not but there is a thumb rule, because most of our 400 kV lines, we say 200 to 300 kilometer range, people use around 16 to 25 MV, NGR value. That is a thumb rule value. But definitely sometimes if you just go with the thumb rule, some cases it may lead to the resonance point. Maybe again you may have to change the NGR value to different value, because see, above 16%, maybe you have the successful order closing phenomena. Okay, but at 16% exactly, if it is any resonance problem is there, but I can go for the 25, right? Then 25% value I can use. So where resonance is not there, and also the main objective of the order closing phenomena is fulfilled.
Thank you so much, Mr. VEERABRAHMAM. The other question is, do we need to consider the same parameters while designing NGT NGR? Okay, the question is from Mr. Tariq.
NGT.
NGT for NGR, yes.
No. There is no NGT in here. NGR. We don't use. That is only for the generator grounding. We use NGTs. So here it is directly connected.
Okay, thank you so much. And is there any other question from the participants? Kindly unmute yourselves and you can ask directly.
Yeah.
And the floor is open to address the questions, and participants are requested to unmute one by one and you can ask your question, please. I guess are participants having any difficulty in addressing it, or if you want, you can type it in the chat box as well. But if there are no further questions from the forum, we can also go towards the closing of the event. Prior to that, we would love to share that we have a feedback link and also the PRDC LinkedIn page that we can share in the chat box. Kindly use that to share your feedback with us. The next webinar is the 24th of December 2020, and the topic will be power system protection using MiPower. The notification will be on our LinkedIn page as usual, and the people can log in and register for the next webinar as well. So, if there are any questions, please let us know. I guess not much questions, Mr. VEERABRAHMAM. Thank you so much for your enlightening session.
I'm extremely sorry from my side this connection problem.
That's
I could
okay.
not-
That is all right.
Okay, fine.
So, for the benefit of participants, you share the information in the chat box. And we would like to appreciate the time and efforts taken by all the participants who are still with us. And we thank all the speaker here and also the organizing committee members, the department heads, and participants from all across, the facilities, industries, and universities and consultancies for being with us and supporting us in all the webinars. And with that note, we would love to thank all of you once again for making this event a great success amidst all types of issues that we had in technical side. A very good evening to everybody, and thank you all so much.